Hey guys, just going to go over these notes very quickly to give you an idea of how these complex numbers work. If you remember from Algebra 2, these conjugate pairs are an important piece. So if you had a 0 right here, I'm trying to circle it a little better, sorry about that. So if you had a 0 that's a plus bi, well then that means that there's another 0 that's a minus bi. So that's kind of why we like complex zeros when we're dealing with all these functions and their polynomials, because if you're given one of the conjugate pairs, one of the conjugate zeros, then you know the other one. And it's just simply by changing the sign in between, in this case our A and our B. So our real piece and our imaginary piece, if you will. So it helps us out as far as locating zeros, whereas last class we had to go through a whole lot of synthetic division in order to determine each one. So this first problem, these kind of moved on me, so make sure I can read it to you real quick, or you can look at it with me, is a polynomial of a fifth degree whose coefficients are real numbers has the zeros 1, so it has one real 0, so we know that if 1 is a 0, then we can write it as x minus 1 as a factor, and obviously that we already know that 0 is 1. And then it also has 5i. Okay, so if it has 5i, that means we can say that obviously that's a 0, and then as a factor we would write x minus that particular 0, so x minus 5i. And as we talked about before, since we know that this is 5i is a 0, its conjugate pair would be the opposite of it, in this case negative 5i. So there's negative 5i. It's one of the other two zeros that we're looking for in our fifth degree polynomial. Well, the way that I like to write these when I write factors is just like I said, x minus 5i over here, because it's x minus the 0 we're given. Or if we're given 1, I say x minus 1, the 0 we're given. We're going to say x minus negative 5i. Now you guys can distribute that negative and make it x plus 5i, that's fine. I just want to make sure that I display it this way, because sometimes it gets a little confusing when you run across some that are 1 plus I, for instance. So 1 plus I is a 0, so we can say x minus 1 plus I. And make sure we put in parentheses, like we did with the negative 5i. Once again, if you wanted to go ahead and distribute your negative, that's fine, but just for display purposes, it makes it easier to see that 1 plus I can be written in parentheses like this with a minus in front when we start kind of listing your factors. So the last one we need to do is for our fifth 0. If 1 plus I is a 0, then we can follow that 1 minus I must also be a 0. And just to follow the pattern we've done before, if we said x minus 1 plus I, we can say x minus 1 minus I. Of course, making sure parentheses are around our 0. So that just kind of gives you an idea, a little bit of how these work. So here's what I want you to try. If you would, after you read example 2, and then pause the video, and here's what I want you to try to do with example 2. Take it a little bit further. Go ahead and write the factors as we did up here above. Okay, obviously it's a little easier because it's a fourth degree instead of a fifth degree. And then I want to see if you can expand it all out and get that, fairly nasty polynomial function written out, in individual terms. So for instance, in this one, if we had done that, we would have started distributing x's and constants and i's and all these different things together, and gotten this nasty x to the fifth and probably an x to the fourth, and so on and so forth. So do the same thing with example 2. So go ahead and pause it, and then when you're ready, go ahead and come back and then see if you got the question right, and we'll talk about it a little bit. Alright, so now let's look at example 2. So if you pause the video, hopefully you got something like this when you worked it out yourself. Let me move this out of the way. Zoom in a little bit, sorry about that, knocked me out. Alright, so hopefully you got x to the fourth plus 6x cubed plus 2x squared minus 26x plus 17. I'm going to go ahead and move all these out of the way so you can kind of see how I got it. So we had x minus 1, like we had earlier. There's x minus 1, x minus 1. negative 4 plus I is a 0, so x minus negative 4 plus I. And then if negative 4 plus I is a 0, then negative 4 minus I is also a 0. And so what I did was I went ahead and expanded x minus 1 and x minus 1, so maybe may have written x minus 1 squared and got this trinomial, and then took these two pieces and multiplied them, and went ahead and distributed by negative first, and then multiplied them together to get this really long line. And luckily these i's will cancel out, and then you have I squared. If you remember from last year, I squared is negative 1. So if we have negative 1 with a negative, that's how this positive 1 popped up. And then it's just a matter of combining like terms. And eventually you'll come to this fourth degree polynomial we have, which has 1, 2, 3, let's see, 5 terms to work with. Alright, so now example 3 is you're going to, for the complex zeros of this polynomial function, and then write f in factored form. So I haven't given you any of the zeros, so the first process you're going to have to do is going through rational root theorem and list out all the possible rational roots that you can go through, and then start picking these numbers and dividing them in using synthetic division until you're able to hopefully find, which you will, a value that works. And then once it works, you're just going to continue to break it down until we can't any further. And obviously, somewhere within there, it's going to be some complex zeros that pop up as well. But we have to knock out those nice zeros first. If you want to try to figure it out completely, go ahead and pause the video at this moment. Otherwise, I'm going to go ahead and give you a hint and let you work that problem out. Okay, so here's your hint. The number you probably want to try first is negative 2. So if you were to work with negative 2 in synthetic division, this right here is going to break down and get to something a little bit simpler to look at. So once again, probably want to pause the video and see if you can break it down with negative 2 and see what happens. So I'll wait until you feel good about that. So you can go ahead and pause right now. Alright, so here's what you should have gotten after you've done all the division. Yeah, can't cover up that 1/3. So just to make sure you can understand what I'm talking about here, when you divide your negative 2 in, there's your 0 that pops up for your remainder. Now, the way I showed it was I went ahead and divided by 1/3, so that's your other nice 0. But, let me go ahead and cover that up again. Right here, if we know this is 3x to the third, negative x squared, 27x minus 9. What I want you to think of that as is if you go and write that off to the side, you can do grouping to factor that particular problem out. But either way, you're going to arrive that 1/3 and negative 2 are our nice rational roots. And what's left over is this 3, which now is 3x squared, and this 27. Well, 3x squared plus 27, we can set that equal to 0 and try to factor it out. Well, if you notice, it's not going to factor out unless we start going into the imaginary numbers, our complexes. Because we can divide by 3 right here, we get our negative 9. And of course, the square root of negative 9 is plus or minus 3i. So that's what the question was kind of looking for, is to write an f in factored form, and then also to list out those complex zeros. Let me zoom in one more time. Sorry about that. So right here, here's our complex zeros, plus or minus 3i. Now it says write f in factored form. It's kind of hard to write it here. I don't have a pen, so I'm kind of doing this by hand. But you would have your normal x plus 2. Okay, and then you would have your x minus 1/3. And so what I've been looking for is how we could write the other pieces. So I would take, one of two things. So there's our zeros, or our factors. You could have written x squared plus 9. Right here, if you divided by 3 and got rid of everything and simplified it, you might have been left with your x squared plus 9. That would be acceptable to write as a factored form. But another way you might write is how we were doing up above, is have your x plus 2 and your x minus 1/3, but now you could write it as x plus 3i and x minus 3i instead of x squared plus 9. And if that seems a bit confusing, we can talk about that next time in class. But those are two acceptable ways of writing it. And I would write that out, but I'm kind of do this on my computer, so I can't really get it very clean. But that's, in a nutshell, complex numbers. So the only thing I need to show you now is application problems. So make sure that you get a paper from the substitute that's talking about application of polynomials if you haven't gotten it already. And I just want to talk about the first question. So I'll meet you there here in one moment. Alright, so the problem that I want to show you with the application of polynomials is number 1. And it talks about this screen door that has a height to width ratio of 4 to 3. So I'm going to come over here. And we know we have a height and a width. And the ratios we're dealing with are 4 to 3. So if you remember, we do this a lot in geometry, but we've done it in this class a little bit too. Those ratios, you can just write it as 4x and 3x. Alright, so let's go back to that question now. So the metal trim around the screen adds 2 centimeters total to the width and 2 centimeters total to the height. Write a polynomial expression that represents the total area of the screen. So it's a bit confusing, not very clear, which is why I definitely want to do this one with you. You have a door, and what they've done is they have a trim. I'll just kind of do that in red just so it stands out, that's around this door. Okay, so a trim is going all the way around it. Okay, and it says that it adds, let's go back and read that again, 2 centimeters total to the width and the height. And so it's saying will be an expression for the area of this entire door, including this trim that's all the way around it. So if our height is 4x, we know that the trim is going to be adding 2 centimeters to that height, so we'll add 2. And then we're doing the exact same thing with our width. It has 3x, and we're going to be adding 2 to that. So these are our two quantities, 4x plus 2 and 3x plus 2. So we put in parentheses just so they kind of stand out. And then it says write an area formula for them. Well, we know that for a rectangular shape, we're going to be multiplying these two quantities. And so just to kind of make it more official, let's go ahead and say A for area. And we're doing this in terms of x. So A of x is equal to 4x plus 2 times 3x plus 2. And then it says to go ahead and simplify it. Really, it's a better way of saying, I think that's what they say. Let me double check it with you. Simplify the expression. So really what I want you to do is just expand it out, multiply it out, and then combine like terms. So you can write that A of x once again, distribute and do all your stuff. And kind of labors here, but you probably can get it way faster than I can writing wise, but 12x squared. Our 4x with 2 would make an 8, and then our 2 and a 3 would make a 6, so plus 14x. And then plus 4 at the very end. And this is kind of the expression that I'd be looking for. There we go. So hopefully that helps you with the applications and just getting you started. Sorry I couldn't be there today, but it's just getting you the notes and just examples that I showed in other classes, and just use this time wisely to work on through these problems. You can now finish the My Math Lab and do those problems that involve complex numbers. And then this handout that you have with applications, this will be due on our test day. You guys have an awesome weekend.